We are now ready to start 6.1, higher degree polynomials.
So let's throw in a few reminders here, just so you know what we're talking about. Polynomials are functions where each term has at most one variable to a positive integer. Where do you got it written? There you go. Now, polynomials can be written in this form, where f of x equals ax to the n plus bx to the n minus 1 plus all the way out to some constant. Now, the degree of a polynomial is the highest variable exponent. And again, the general format is that they're in descending powers. For example, we might have 7x to the 5th plus 9x to the 4th minus 8x squared plus 7x plus 1. Notice it doesn't have an x to the 3rd or an x cubed. It just has to go down in order. The leading term and the leading coefficient is the first term and or coefficient in general format. Okay. So again, that leading term will have the highest degree. End behavior. When asked to describe the end behavior of a function, we are determining where the output, okay, which we often think of as the y, where the output is approaching as we go out left and right. So the notation for this, we might say as x is approaching positive infinity, f of x is approaching something, question mark. And as x is approaching negative infinity, in other words, going to the left, our function f of x is approaching what? So as our x is going right, or as our x is going left, our y is going where? So let's do a couple examples. We want to give the end behavior of these following two graphs. The nice thing about end behavior is we don't care what's happening in the middle. Okay, we're only looking at the arrows at the ends as we're going left to right. So in this first example here in A, we can focus to the left. Let's say as x is going towards, we can do the negative infinity first. As x is going towards negative infinity, and they're in this direction here, where is our y going? It looks like our y here is going down towards negative infinity. So as x is going towards negative infinity, f of x is also approaching negative infinity. Then as x is approaching positive infinity, in other words, x is going out this way, as x is getting larger, our y is also approaching negative infinity. Since they are both approaching negative infinity for your y values, you could write it as x is approaching positive or negative infinity. In other words, you're looking at both directions. F of x is only going towards negative infinity. So you can combine it like that, but only if your graph is going in the same direction, both ways. If we are looking at this function here, let's focus as x is going towards the left. As x is approaching negative infinity, which is this direction here, I want you to notice that the y isn't approaching positive or negative infinity. It's not going up or down. It actually seems to be getting really close to this y value, which is 1. So look more towards that horizontal value. Is it going up and down, or is it going left to right? Okay, so it's approaching a y value of 1. So f of x is approaching 1. Now let's do the right-hand side. As x is approaching positive infinity towards the right, well, this guy seems to be approaching the x-axis, which has a y value of 0. So f of x is approaching 0. Because the y values are approaching two different numbers, I can't combine them, as x is approaching positive or negative infinity, because they're going towards two different values. Now, here's something to note. Polynomials will always follow the end behavior of its leading term. And this is going to be very helpful when you're given certain equations instead of graphs. For example, even polynomials have an even degree, like x squared. If the leading coefficient is positive, then it's going to open up regardless of what it does in the middle. Doesn't matter if it's an x squared or an x to the 8th. It might do something weird in the middle, but it will always open up like an x squared. So as x approaches either positive or negative infinity, our function value is going to be going towards positive infinity. If the leading coefficient is negative, then that means that polynomial, regardless of what happens in the middle, will eventually be going downwards. It opens down. So we can say as x is approaching positive or negative infinity, f of x is approaching negative infinity. So if we have a polynomial, then we can just look at the first term and already know the end behaviors. We do not have to graph it. Likewise, for an odd polynomial, these have an odd degree, like x cubed. And remember, our cubes look like this. That's why it's nice to know kind of what parent functions look like, right? X squared is a parabola. X cubed has that nice little swirly-do. So for an odd polynomial, if the leading coefficient is positive, then regardless of what happens here in the middle, it's going to increase from left to right. So as x is approaching negative infinity, f of x is also approaching negative infinity. As x goes towards the right, towards positive infinity, f of x also goes towards positive infinity. Now, if your leading coefficient is negative, that odd polynomial, regardless of what happens in the middle, will eventually decrease overall. So that means as we go towards the left, as x approaches negative infinity, f of x goes towards positive infinity. And as x goes towards positive infinity, f of x goes towards negative infinity. It's the opposite. So again, this means we do not have to graph polynomials in order to determine their end behaviors. We want to describe the end behaviors of the following polynomial functions. If you want to pause the video and try these on your own and then see if you get the same answer, awesome. Otherwise, we can do them together. So on A, notice we're going to look at our first term. This is an even degree polynomial, and since 3 is positive, that means it's going to open up like a parabola. So here is our answer. As x approaches positive or negative infinity, our function value is going towards positive infinity. In other words, it's increasing, going up. So this is actually the answer. Everything else just kind of helps us get that answer. For B, looking at end behaviors, we only need to look at our leading term because as x gets really large, 9 becomes insignificant. Even 4x and x squared becomes insignificant compared to x to the 5th. You know, a billion to the 5th power will overtake a billion squared or anything else. So that's why we look at the leading coefficient. So this is an odd degree, and since that leading coefficient is negative, that means it's going to be decreasing. So that will help us with our end behavior. As x goes towards negative infinity towards the left, the function is going up towards positive infinity. As x is approaching positive infinity towards the right, f of x is going downwards towards negative infinity. That's the end behavior. For C, again, it is odd. Leading coefficient is positive, so it's going to be increasing. So as x approaches negative infinity, f of x is also approaching negative infinity. And as x is approaching positive infinity, f of x is approaching positive infinity. And D, looking at our leading coefficient, it's even, so it'll look like an x squared. It has a negative coefficient, so that means it's going to be opening down. So as x is approaching positive and negative infinity, f of x is going down towards negative infinity. So that's it for end behaviors of the polynomials. So local behavior is more what's happening in between the ends. So when asked to describe the local behavior of a function, we're looking at the middle of the graph and determining where the graph changes behavior. Particularly, we're finding the intercepts. Those are important points. And turning points. So what's a turning point? A turning point, or what's called a local max or min, is the point where a graph changes from increase to decrease or vice versa. So for example, if we have a polynomial that's doing this, this is a turning point, this is a turning point. You can consider it like those inside vertexes, a local max or min. Now, a polynomial whose highest exponent is n other words, has a degree n, has at most n zeros and n minus 1, put that parentheses, n minus 1 turning points. If you forget that little piece of information, think of x squared, okay? So our n is 2. So for any parabola, you will have at most 2 x-intercepts or zeros and 1 turning point. Now again, it means at most because that parabola could have no zeros. The whole parabola can be above the x-axis and never touch it. Okay, so it's at most n zeros and 1 less than that turning point. So here's a couple of things that you guys can practice on your own. If you want to pause it and give these a shot. Otherwise, we can do them together. You want to draw an even degree polynomial with 4 zeros and 3 turning points. So remember, an even degree has to eventually be facing the same direction. Either the ends all go up or the ends all go down. So if we need 4 zeros, there's 1 x-intercept, 2 x-intercepts, 3 x-intercepts, 4 x-intercepts. Okay, and it's even, it's going in the same direction. So there's our 4 zeros with 3 turning points. 3 turning points and 4 zeros. Next example to the right, we want to draw an odd degree polynomial with 3 zeros and 4 turning points. So remember, 3 zeros, 1, 2, 3. So that looks like an odd polynomial with 3 zeros. But right now, it only has 2 turning points. So we need 4 turning points without it crossing the x-axis again. We can do that. 1, 2. So now it has 2 more turning points without adding any zeros. But it's still an odd because it's going in 2 different directions with the end behavior. Now let's see if we can draw an even degree polynomial with no zeros and 3 turning points. No zeros just means it never crosses the x-axis. So we need the entire thing below or the entire thing above. We need 3 turning points. So there's 1, 2, 3. 3 turning points. But no x-intercepts, no zeros. Now let's draw an odd graph with 2 zeros and 2 turning points. This can be tricky. What this means is one of those zeros is going to just touch the x-axis. So here's 2 zeros, but one of those zeros is also a turning point. 2 zeros and 2 turning points. So remember, an intercept is where it crosses or touches an axis. It could just touch it and bounce right off. So let's take a look at these graphs and see what degree they possibly could be. For example, we know this graph in the top left has to be even. It has 1, 2, 3, 4 x-intercepts. So it could be of degree 4. Matter of fact, that is the smallest degree that it could be. Because remember, it could have at most n zeros. For this next example, we have 3 zeros, but 4 turning points. So if there are 4 turning points, remember our turning points have n minus 1 turning points. So this would be a smallest degree would be 5. This bottom left has 3 turning points and it's even. So its smallest degree would be 4. And this is an odd graph with 2 zeros and 2 turning points. So we have a smallest degree is 3. Last but not least, we want to write the equation of the odd degree polynomial with zeros -2, 1, 4, and a y-intercept of 0, 2. So this is similar to what we were doing with the quadratics. We have a polynomial. If it is in factored form, we would have a times x plus 2, because it's minus the -2, x minus 1, and x minus 4. Remember, that's how we can find those x-intercepts or those zeros in factored form. The only thing now is we have to find our a. So we can use that other point, 0, 2, plug it in for our x and our y, and solve for our a. And again, it does not have to be the y-intercept. It can be any point. It's just the y-intercept is nicer if you know it, because plugging in 0 for x makes it faster. So we get 2 equals a times 0 plus 2, 0 minus 1, 0 minus 4. So 2 equals 8a. A equals a positive 1/4. So our odd degree polynomial would be 1/4 times x plus 2 times x minus 1 times x minus 4. And again, there's no need to multiply it out unless they've asked you to. We know it's going to be an odd degree because there are 3 x's being multiplied. You're going to get an x cubed. All right, that is it. I am so proud of you guys. Keep up the good work. Come and see me if you need help. Bye.